So we will need the following result. This is, we are discussing condition probability so far. So we will need the following result. So this is theorem 1.3.5. I will need this. So maybe I should change the text back to something. Theorem 1.3.5. Here the idea is that I may have many events in my portfolio. So I may have one event of interest. So let A be an event. So think of A as the event of interest in sample space S. With probability P. P. And then you let B sub I 1 less than equal to I less than equal to N be a disjoint collection of events for which probability of B sub I is positive for all I. That's the setup we have. And let's assume also further that the event A is contained in the union of I equal to 1 to N of the BI. So all your BIs sort of contain your A. So you're partitioning the sample space in some way with BIs, and your A is contained in it. Suppose probability of BI and probability of A given BI are known. So I know that, like in the previous example, I could compute probability of A given B and probability of B. Once you know this, then there's a nice way, this is going the reverse way. So then probability of A may be computed using these two conditional probabilities. So the probability of A is the same as the sum from I equal to 1 to N, probability of A given BI times probability. So the idea is that to go reverse. Suppose I know probability of B and BIs and probability A given BIs. Can I compute the probability of A? So this is a reverse idea. So you just pause a minute and think about the case n equal to 1. It will be obvious because A is contained in B, and it's obvious from definition. But otherwise, let's do it step by step. So all you do is, sorry about that, let me get the blue. So I have BIs. It's still black. Very good. So I have BIs I equal to 1 to N are a disjoint sequence of events you already know that. So this implies what does this imply? This will imply A intersection BI I equal to 1 to N are also a disjoint sequence of events. Because if BI is a disjoint, there's no common element in the BIs, There will be no common element in the A given B. So now this will imply the following, right? It will imply that for the axiom of probability, or more or less the I think it's equation 2 in this theorem 1.1.4. Let's go 1.1.4. We write that in green, so it's clear that we are useless. And we prove this fact that probability is finitely additive. So that probability of A is the probability of union I equal to 1 to n, A and Bi, and that's the same as the sum from I equal to 1 to n, probability of A and Bi, because they are disjoint sequence of events. But now you look at this way. So now you know the following, right? The probability of A given Bi, by definition, was going to be probability of A and Bi, A and Bi divided by probability of Bi. This we know by definition. But that's the same as probability. That's same as saying probability of A and Bi is equal to probability of. If I let me do step by step. This part. Again, this whole thing is happening. Let's go back. That's same as saying that this is same as saying would imply probability of A and Bi is the same as probability of A given Bi times probability of Bi. So therefore, what do we obtain? You apply this in star. Let's call this in star. So you apply in star to get what? To get probability of A is the same as the sum from I equal to 1 to n, probability of A given Bi times probability of Bi. And that's what we want. So this is true for all I. That's right. So a simple idea that if you have, if you know conditional probability, you can recover the original probability as well, and vice versa. This is kind of useful idea to have. Okay. So let me do an example to illustrate this idea. Suppose we have three boxes. And in the three boxes we have, let's say, a collection of balls. So we have three boxes. Let's say three boxes: box 1, box 2, and box 3. There are three boxes, and in each of these three boxes, let's say I have three sets of balls. Okay, so sorry about that. Let's say I have a blue sort of blue balls. Let's say I have blue balls here. This now. Go here. So I have blue balls. Let's say I have 5 blue balls in one box, 2 blue balls in the second box, 3 blue balls. And let's say I have a bunch of red balls. So red balls I have, let's say I have 4 red balls, I have 3 red balls, I have 3 red balls. And let's say I have green. I have green. Let's say I have 3 green balls in this box, and 3 in this box. Let's say I have 4. I forgot to put the red in this one. Let's say I put 3 red in this one. So 4, 3, 3, 3, 3, 4, and 5, 2, 3. That's what I have in the box. Now what I do is, the experiment I do is, I choose a box at random. That means I choose one of the boxes in an equally likely manner. And from that box, choose a ball at random. So when I mean this, I just mean that I'm in this equally likely outcome setting. So that's all I mean. Right? This means that we are in this equally likely outcome setting in both cases. As each box is equally likely to be chosen, and each ball is equally likely to be chosen. So once I have it, so then the question I ask you is the following: what is the chance? What is the probability that a red ball is chosen? So how does one do this? So what are you choosing a box first and then choosing a ball next, right? And then I want to know the end result, that I have a red ball that's chosen. So how does one do this? So what one does is, let's say set up notation first. Let's say R be the event that a red ball is chosen. And let's say BI be the event that box I is chosen for I equal to 1, 2, 3. And now you observe a little bit carefully. So now if you look at this above calculation, oh, what happened to my 3 again? My 3 again is gone away. Why keep going? Our calculation, see, these are 3 boxes and so on and so forth. Now if you look at this, if I go to box 1 and I try to choose a ball and I want it to be red, I have how many? 4 plus 3 plus 5. That's like 7 and 12, and the chance to getting a red ball is 4 by 12. So that means the observation is that probability of red given B1, that means there are 12 balls there, and there's 12 in total, and I have 4 likely red balls, so that means 4 by 12. Probability of red given B2, if I go to box 2, I have 3 plus 3 plus 2, that's 8 at the bottom, and I have 3 favorable guys. And probability of red given B3 is going to be again equal to, I have 3 plus 4 plus 3, that's 10, and I have 3 is my, I have 3 at bottom, my favorite event. And I also know, this is one possibility, and I also know the chance of B1 is equal to chance of B2 is equal to chance of B3 is equal to 1/3. Both these things I know for sure. That's just from the model, right? So I have 3 boxes. Once I pick a box, I know these conditional probabilities, and I know I pick each box with these things. So now we are in the setup of this theorem. So now we also know the following: the event R is also contained in the event of union I equal to 1 to 3 BIs, because just once a box is chosen, you choose a ball from that. So red ball is chosen is contained in that. So you apply theorem. One point 3.5. What do you get? You get probability of R is equal to the sum I equal to 1 to 3, probability of R given BI times the probability of BI, and that turns out to be what? That turns out to be, you go and plug in all the calculations, right? This sum is 4 by 12 into 1/3 plus 3 by 8 into 1/3 plus 3 by 10 into 1/3. You do the whole calculation, and then you'll end up getting something like, I think, It's 36, 24, 30. I think 360 is the LCM. I think it's 121. Chance showing a red ball is 121 by 360. So that's one simple calculation one can do. Now the same example, suppose I twist a little bit. So suppose I take my favorite event R. Okay. So let's say I want to understand, given that the red ball is chosen, can I find the fact that the third box was, it came from the third box. So given the red ball is chosen, can we find the probability that it was chosen from box 4, box 3? So what do I want to find? So the in probability term, that is, you want to find the conditional probability of B3 given that a red ball was chosen. So now this is sort of intuitive, right? Because now I'm going reverse. So here I went forward. I said I had these boxes, I had these collections. I knew the R given B1, R given B2, and R given B3 because that's the conditional probability of an equal likely experiment. So I know exactly what's going on. And then I want to know what the probability of R is. That was easy to do. But now I want to go the reverse. I want to find probability of B3 given R. So what you do is you do a little trick. So probability of B3 given R is the same as what? Its definition is what? Its definition is B3 and R divided by probability of R. This you already found out, probability of R. The top you have to find out. But top you just flip it a little bit, right? You just flip it as probability of R and B3. That same event divided probability of R. But that's the same as probability of R given B3 times probability of B3 divided by probability of R. So you know both these things, but that you know exactly what's going on. You know R given B3 is 3 by 10, right? That's what we did before. Let's go back and check. R given B3 is there are 10 balls and 3 of them are black, red, so 3 by 10. Come back down. Probability of B3 is 0.1 over 3, and probability of R, which is calculated as 121 by 360. So you do this, and then you get 36 by 121, and that's the same as something like 0.29. Therefore, the conditional probability of choosing box 3, or let's say conditional probability that that box 3 was chosen or B3 occurred, given that R occurred, that is the red ball was chosen, is around 30%. So just one observation before I do this whole go on to the general setup of this idea. The idea is quite general. So the idea was that let me go right now. So the idea was that we wanted to know probability of B3 given R, right? And then we did some calculations, and then we turned out that we got it as probability of R given B3 times probability of B3 divided by probability of R. This is just a standard sort of calculation. Then if you notice in the earlier step, earlier step, what we did was we already done this. The top we had probability of R given B3, that's already there, that we knew, and probability of B3. And we had done this following thing, that to calculate probability of R, we had done this as summation I equal to 1 to 3, probability of R given BI times probability of BI. That is what we had done. So this crucially we use this idea. So this exactly we didn't use chance that okay, we could have skipped this step. So this step is kind of skipped. So if we, even if we didn't want to do this step, we could have just done the last step. Right? This is what we used, and that's sort of so we do all the conditional probabilities and the probability of BIs to get the reverse conditional probability, that is of BI given B3 given R. So this is a part of a good theorem in probability called Bayes' theorem, which I'll state next. Okay. So here's this theorem. So theorem is the following. Let me write in black as before. Let's keep convention straight. Theorem 1.3.1. Suppose A is an event and BI such that 1 less than equal to I less than equal to N are a collection of disjoint events. Oh, sorry, I have to use blue, so let's go back and fix this. Okay, let me leave that part in black here. Little disjointed notes, etc. Disjoint events whose union contains A. So here, so let me just make it blue so it's consistent. Suppose A is an event and BI 1 less than equal to I less than equal to N are a collection of events whose union contains. That is, A is contained in a union I equal to 1 to N of BI. Let's assume A's probability of A is positive and probability of BI's are positive. I equal to 1. Then for any 1 less than equal to I less than equal to N, probability of BI given A is the same as probability of A given BI times the probability of BI divided by the sum from I equal to 1 to N. Let me put the J so that the index is clear. J equal to 1 to N, probability of A given Bj times the probability of Bj. This is true for all I between 1 and N. So if you know probability A given Bi's and Bi, you can get probability Bi given. So proof already we have done in some sort in the previous step. I'll just rewrite the proof properly and I'll close with that. The proof is the following. So probability of Bi probability of BI given A, again we know the same as probability of A and BI divided by probability of A. Right? This is just conditional probability. So we fix an I between 1 and n. This is true by definition. So by definition, this is true. Now that's the same as, again, like we did before, this BI and A divided by probability of A. Now you do two steps. So think of this as probability of A given BI times probability of BI. This is by definite probability. And the bottom, you use the theorem 1.3.5, which says that the same as j equal to 1 to n, probability of A given Bj times probability of Bj. It's a simple idea. So the bottom we have used this theorem 1.35. Right? So what have we done? We have used two things. In the top part, we have used the definition of conditional probability. And the bottom part, we've used this theorem 1. That finishes off the proof. That's simple proof of base theorem. But this is kind of a powerful theorem. So we'll illustrate. This is originally due to it's called Bayes theorem. So you should write it down in green. It's a mathematician called Thomas Bayes. It's called Bayes theorem. And I think it was the early 1700s. Of course, it's not in this notation, but probability notation, the formal probability notation came much later. So let me do an example, and then I'll close it. Example of 1.3.12 is the following. So let's say this is probably relevant in the current day terms in terms of what's happening in the world. So Sham, let's say, Sham is randomly chosen. From, let's say, from citizens of Hyderabad, let's say. Right? And let's say he's given a test for swine flu. Okay, so to test for swine flu. So we have three facts. Let's say it is found 95% of people with swine flu test positive. Okay? So you give a test for the disease. You give a test. The test has this rate of 95% where it detects correctly. We also found that 2% of people without the disease will also test positive. There's a sort of a false sort of positive coming up. Then we also know 1% of the population, let's say, has the disease. This is what we have, right? So then I do this. I tell you that Sham tests positive. So let's say Sham tests positive. Suppose Sham tests positive. what is the probability that what is the probability that Sham has the disease? Is that clear? So I have this example where I have to do this test to people. The test is 95% in sense true. If the in 90% of people, it'll test positive for the disease. With the, who have the disease will test positive. 2% without will test positive. In the population, it's 1% prevalence. What's the probability Sham has it? So yes, it's a very applicable problem. So what do you do? Define two ways. You define an event A that the event A is that Sham has flight. Sham has flight. That's the event A. Okay. B is the event that Sham tested positive. So what all do we know from the top? Let's go to the top. Let's see what all do we know in terms of A and B. So we know that 95% of the people with swine flu test positive for the disease. It means from let's call this observation as one assumption, assumption 2, and assumption 3. Right? So from 1, I know what do I know? I know the chance that Sham tested positive, given that he has the disease that is given A, is going to be 0.95. That's what 1 tells me. What does 2 tell me? 2 tell me 2 tells me that 2% of people without disease will have be positive. It means the chance that Sham tests positive, given that he does not have the disease, that's going to be 0.002. And what does 3 tell me? 3 tells me the chance that Sham has the disease is 0.1, 0.0. And what do I want to compute? I want to understand the fact that Sham tested positive. What chance is the disease? That means what's the chance that Sham has the disease given that he has tested positive? So it's applying Bayes' theorem for the 2 case. So you apply Bayes' theorem and finish the problem. So you know by Bayes' theorem, probability of A given B is the same as probability of B given A times probability of A divided by probability of B given A times probability of A plus probability of B given A complement times probability of A complement. And that if you work out the mathematics, so you put the mathematics down, so what do you only have? You have B given A is 0.95 and probability of A is 0.01. Whole thing divided by B given A is 0.95 times 0.01 plus probability B given A complement is 0.02 times A complement is 0.99, and that if you do, it comes out to be 0.324. So that means chance that Sham has the disease given that it is positive is only 0.324. So that's not kind of a bad test. So a couple of things to note. So this is an exercise of how I applied Bayes' theorem. So to check assumptions, I didn't check that. But all the events are positive probability, so the whole thing works out. It's by a Polish mathematician called George Polya. So it's widely applicable, even though I will not explain the applications in this class. So these appear. This is a very simple model. It's called the Polya's urn, I think. and it's very widely applicable. Even though the example is very simple. So suppose an urn contains R red balls and let's say B black balls, B blue balls. So let me B black balls. So R red balls and B black balls. Forget it. R red balls and B black balls. Now, what you do is the experiment is the following: a ball is drawn at random. So it's crucial. A ball is drawn at random. And it's color noted. Okay. And then the crucial part is after this, it is replaced. So you remove the ball, but it's replaced with C positive balls of the same color. Is that clear? So then this is step one. Then you repeat this step. The procedure repeated. Each time you pick a ball, you note its color down, and then you just replace the ball with C of the same color. Now let's say R1 is the chance that a red ball was drawn in draw 1. In first draw. So again, and let's say R2 was the chance that a red ball was drawn in the second draw. So now let me try and see if it works. No. Then let's see. Then now let's say B1 and B2 are respectively the same thing. So that is a black ball was drawn in the first draw. And similarly here, a black ball was drawn in the second draw. Suppose that was the case. Now let's do some simple calculation. So now the probability of drawing a red ball in the first draw, right? That's easy, right? So you have B plus C, B plus R amount of balls, and you want to choose red. R is red. That's just R by B plus R. That's easy to show. That's straightforward. Now let's try and do probability of R2, right? R2. Probability. What are R2? So now again the same way, right? So the same as the probability of R2 and R1 is draw first one, or R2 and you pick B1. Right? That's what happens in the first draw. You either pick a red ball in the first draw or a blue ball or a black ball in the first draw. So again, this is the same as the probability of R2 and R1 plus probability of R2 and B1, and the whole thing is write down same as R2 given R1 times probability of R1 plus R2 given B1 times probability of B1. So let's go back up here. We know probability of B1 is going to be equal to B by B plus R. That's easy. Now what's happened here in these two steps? Let's see. Let's do 2 steps. How do you do probability of R2 given R1? So in this case, what would you do? You've chosen R1, you've chosen a red ball, right, in the first draw. So for the second draw in the box, for second draw in the box, there's going to be, you've chosen R1 in the first draw, so it's going to be R plus C red balls and B black balls. That's what's happening in this setup. This probability is going to be equal to here. If I do this calculation, so I'm going to get R plus C choices I have, and I divide by R plus C plus B. That's what I get here. This percent right here I already know from the previous step. That is just probability of there's B by B plus R. Now, if I come here with this person right here, let me come down this way, right? Here, if I come down, it's not a good idea. Let me go this side. If I come all the way down, here, for this person, in the second draw, what all do I have? In the second draw, I've chosen B1, it means I've chosen a black ball in the first draw. That means I have R red balls, and I have B plus C black balls. That's what I have in this case. Right? So this person right here would just come down to be, I have only R at the top, right? And I have R plus, I have B plus C. Right? But B plus C are numbers, doesn't really matter. And this is just going to be, so it's R by, I made a mistake here. This is R by B plus R because red ball, and this is B by B plus R. So now I do the jugglery now. I just write the mathematics down. So that's same as, so I have R, I have the denominator is the same. So I have this divided by, I have R plus C plus B into B plus R. That's on both sides, so that's easy. So top I have R into R plus C in the first term, plus I have R into B in the second term. This is what I get. So now if I remove the R out, so it's R into R plus B plus C divided by R plus B plus C, and I have another R, another B plus R here. So these two cancel off, and I get R by B plus R. I get the probability of R2 is also R by B plus R. So it's kind of a very, very interesting model. That is, if you do this experiment where you when you keep adding balls the same color, then it so happens that the probability of choosing a particular color doesn't change. It's a sort of an interesting sort of aspect of this model. It's called Polylearn Scheme, and one can actually check that this is true for any draw. In fact, one can actually check this. So let me just write that down. So the remarkable feature of this model is that one can actually check that one can actually check it is true that probability of Rj in fact is is R over B plus R for all j bigger equal to 1, given on the first one which I verified.